Welcome to today's paper reading. Today's paper is titled, MagicDec, Breaking the Latency Throughput Tradeoff for Long Context Generation with Speculative Decoding. This paper was published on the AR14 preprint by Jian Chen and colleagues from Carnegie Mellon University, Moffat AI, and Meta AI FAIR. Large language models, LLMs, are increasingly used in long context applications like interactive chatbots, document analysis, and agent workflows. However, serving long context requests with low latency and high throughput is challenging. Speculative decoding (SD) is a technique used to reduce latency without sacrificing performance, but it is traditionally thought to be effective only for small batch sizes. In MagicDec, the authors demonstrate that SD can achieve speedup even in high throughput inference regimes for moderate to long sequences. They also show that an intelligent drafting strategy can achieve better speedup with increasing batch size. MagicDec identifies bottleneck shifts with increasing batch size and sequence length, and uses these insights to deploy speculative decoding more effectively. It leverages draft models with sparse KV cache to address the KV bottleneck that scales with both sequence length and batch size. This underscores the broad applicability of speculative decoding in long context serving, enhancing throughput and reducing latency without compromising accuracy. For moderate to long sequences, MagicDec demonstrates up to 2x speedup for Llama 2-7B32K and 1.84x speedup for Llama 3.1-8B when serving batch sizes ranging from 32 to 256 on 8 NVIDIA A100 GPUs. The landscape of language models has evolved significantly, with models now capable of processing extremely long context lengths. This evolution has introduced new demands, such as the need for low latency in interactive use cases like chatbots, and high throughput in background data processing workloads. However, achieving both high throughput and low latency simultaneously remains a significant challenge. Speculative decoding (SD) has emerged as a technique to improve latency while maintaining generation quality. It uses a fast draft model to generate multiple tokens, which are then verified by a larger language model in parallel. Despite its promise, SD has been believed to be less effective in improving throughput with larger batch sizes. This work challenges this conventional belief, aiming to demonstrate that speculative decoding can indeed improve throughput, reduce latency, and maintain accuracy, especially for longer sequences. Figure 1 illustrates the relationship between throughput and latency for TinyL Llama 1.1b speculating Llama 2-7b32K at various prefill lengths. Part A shows the throughput of both autoregressive decoding and speculative decoding, SD, against per token latency for a prefill length of 8,000. Part B presents the throughput ratio of SD to autoregressive decoding across different latency budgets, demonstrating that SD enhances throughput for sequences longer than 1024 tokens. This figure highlights the effectiveness of speculative decoding in improving throughput for longer sequences without compromising latency. In the realm of optimizing large language models, LLMs, several methods have been developed to enhance both latency and throughput. System-level optimizations such as flash decoding ++, and faster transformers have been instrumental in improving latency. On the other hand, speculative decoding has emerged as a novel sampling algorithm designed to speed up inference, particularly effective for long sequences. Additionally, batching techniques like continuous batching and chunk prefill have been proposed to improve GPU utilization and handle heterogeneous batches with varying context and generation lengths. These methods, while effective, do not address the memory-bound issues of autoregressive decoding, which our work aims to complement by focusing on homogeneous batches. The theoretical model for estimating the speedup using speculative decoding, SD, involves several key parameters: the speculation length gamma, the batch size B, and the sequence length S. The time taken by the target and draft models to decode one token is denoted as TT and TD, respectively. The verification time TD depends on the number of speculated tokens gamma. The expected number of tokens generated in one verification step, omega, gamma, alpha, is a function of the acceptance rate alpha and speculation length gamma. The total speedup from speculative decoding is influenced by three primary factors: the draft-to-target cost ratio TD/TT, the verification-to-target decoding cost ratio TV, gamma/TT, and the expected generation length omega, gamma, alpha. Our analysis identifies a critical sequence length inflection, beyond which the speedup tends to increase with batch size. This is due to the shift in bottleneck from compute to KV cache loading, which becomes more dominant with increasing batch size. The draft model design, particularly the use of sparse KV cache, can significantly impact the speedup, especially for long sequences and large batches. Figure 2 presents a theoretical analysis and expected speedup for the Llama 2-7B32K and Llama 3.1-8B models deployed on 8x100 GPUs with a speculation length gamma equals 3. The figure includes subplots showing the theoretical draft time to target time ratio, TD/TT, versus batch size, and the theoretical expected speedup with self-speculation for a budget of 512 across different batch sizes. This analysis is crucial for understanding the performance trade-offs and potential optimizations in large language model inference. Figure 3 provides a theoretical analysis of the KV cache bottleneck in speculative decoding. Panel A shows the time breakdown for Llama 2-7B across different batch sizes, focusing on KV cache, waits, activations loading, and compute times. Panels B and C illustrate the draft-to-target memory ratio against batch size for various sequence lengths, specifically for the Llama 3.1-8B/Llama 3.1-70B and Llama 2-7B/Llama 2-70B architectures. This analysis helps in understanding the impact of batch size and sequence length on memory usage and computational efficiency in speculative decoding scenarios. Figure 4 presents a theoretical analysis of self-speculation for Llama 2-7B and Llama 3.1-8B models with a draft streaming LLM budget of 512 and a batch size of 256. Part A shows the ratio of target draft latency versus sequence length for Llama 2-7B32K with a fixed speculation length of 3. Part B illustrates the theoretical speedup for different sequence lengths with a fixed acceptance rate of 0.8. Part C demonstrates the theoretical arithmetic intensity for various sequence lengths and different models. These analyses provide insights into the performance and efficiency of speculative decoding under different conditions. In this section, we address the issue of the KV cache becoming a bottleneck as batch sizes and sequence lengths increase. To mitigate this, we propose the use of accurate draft models with a constant KV cache. We adopt streaming LLM for our draft models due to its simplicity and effectiveness. This method uses attention sinks and a sliding window KV for attention computation, allowing for a stable, training-free approach to handle infinitely long contexts. Additionally, we leverage target models with streaming LLM cache for self-speculation, as the KV cache, rather than model weights, becomes the major bottleneck. Our theoretical analysis in Figure 4 shows that the relative cost of self-speculation draft approaches 0 for large sequence lengths with a fixed budget of 512. The experiments demonstrate that speculative decoding consistently achieves better performance than autoregressive decoding, especially with increasing batch sizes and sequence lengths. This aligns with the theoretical analysis. The optimal speculation length, denoted as optimal, shows consistent improvements in speedups, which can vary with batch size and is influenced by the type of GPU used. For instance, the NVIDIA H100, with its higher flops-to-memory bandwidth ratio, shows better speedups compared to the A100. This is due to the H100's higher compute bandwidth reducing the time for decoding, resulting in better overall speedup. Figure 5 illustrates the end-to-end speedups achieved for different target draft pairs across various streaming LLM budgets, specifically 256 and 512. The annotations indicate the optimal gamma value, denoted as optimal, which corresponds to the highest speedup achieved. For the Llama 2-7B32K model, gamma ranges from 1 to 4, while for the Llama 3.1-8B model, It ranges from 1 to 5. The figure highlights how speedups vary with different batch sizes and sequence lengths, providing insights into the optimal configurations for maximizing performance. Table 1 presents a detailed comparison of results across various configurations of Llama models, specifically focusing on the Llama 2-7B32K and Llama 3.1-8B models. The configurations are set with a budget of 512 and a gamma value of 2, utilizing 8 times A100 GPUs. Key metrics analyzed include gamut D, target draft latency, TV, verification latency, omega, acceptance rate, TAR, autoregressive latency, TSD, speculative decoding latency, and X, speedup factor. These metrics provide insights into the performance and efficiency of speculative decoding versus autoregressive decoding under different prefill lengths and batch sizes. Table 2 presents the results of performance comparisons on L40 and H100 hardware. It highlights a significant 2x speedup achieved by the Llama 2-7B32K model with a sequence length of 32K and batch size 32, as well as a 1.84x speedup for the Llama 3.1-8B model at a sequence length of 100K and batch size 32. These results underscore the impact of sequence length and batch size on the performance, aligning with the maximum KV size constraints detailed in the experimental setup. In this work, the trade-off between throughput and latency in long context scenarios is reassessed. The authors demonstrate that speculative decoding can significantly enhance throughput, reduce latency, and maintain accuracy. Their theoretical and empirical analysis shows that as the sequence length and batch size increase, the bottlenecks shift from being compute-bound to memory-bound. This shift allows for the effective use of speculative decoding for longer sequences, even with large batch sizes, achieving up to 2x speedup for Llama 2-7B32K and 1.84x for Llama 3.1-8B on 8A100 GPUs. More surprisingly, larger batches can achieve even better speedup from speculative decoding if draft models with sparse KV cache are used. These results underscore the importance of integrating speculative decoding into throughput optimization systems as long context workloads become more prevalent. Thank you for watching.